Okay, so here's the last thing that we talked about, and we spent really the bulk of the time talking about this theorem, probably the bulk of the time actually proving it. It was a rather arduous task. It's a powerful theorem, so let me give you an example. What this theorem says is something that seems obvious and is obvious for final sets in a certain sense. In fact, you can even use ordering to do this. But this is even true for infinite sets. Sometimes it is hard to get a one-to-one and onto match to make B. What this theorem says is if you can get a one-to-one match from A to B and one-to-one match from B to A, you're good to go. That's all you have to do to show there. Then there must exist a bijection. Hopefully you all have seen from the homework enough that this is actually not so easy necessarily because it says two endpoints on it. This doesn't. Right? Can anybody give me a one-to-one map from 0, 1 into 0, 2? So let's closed interval from 0 to 1 into the open interval from 0 to 2. Yeah, how can I go 0, 1 and put it inside 0, 2? How wide is this interval? 2. How wide is this one?
1.
Looks like it will fit. How can I make it fit as easily as possible?
And add 1, how 1 half to everything.
Good. Why not 1?
Then you end up smooth and fun.
Good. Just kick everything up by 1 half. Right? This takes this in a one-to-one fashion into the interval from 1 half to 3 halves, which sits inside here. That's a one-to-one. Everybody agree? How about, and proving this is one-to-one is easy. It's too wide. What can I do?
Half left.
And now this is fixed. Right. And this is also one. So the size of these are the same by the Cantor-Schroder-Bernstein. Right? That's magic because go ahead and try to find a bijection between those. You can do it, but it's obnoxious. It's a pain. Okay, so let me give you a corollary to this. A, B, and C are sets. If the symbol for this means 9. So if there's a one-to-one map that goes from A into B, then it's not the case that any one-to-one map from B into A has to be well, there has to exist. It can't be the case that B is strictly less than A. If Someone think we do some role reversing here. And the C, then cardinality is strictly less than cardinality C. And 4. Okay. So I'll leave that for you to kind of cogitate. We are going to do one last bit on this kind of set theory, kind of fundamental foundations part of this course, if you will. Just out of curiosity, how many of you have ever heard of the axiom of choice? Right. Basically, it's about choice. What it means is if you've got some collection of sets, you can, this is very informal, you can go through that collection of sets and select out any elements that you want, right? Maybe my two sets are people on this side of the room, people on this side of the room, and there's a choice function I can go through. I can pick you out of this set, I can pick you out of this set, and make my choice. This is not anything that's going to mess with your brain for a finite number of sets. In fact, there's nothing. But if you have to make infinitely many choices, it gets maybe a little bit more dicey. And of course, comparability is about comparing perhaps sizes of sets. Let me give you this following theorem. Which you might think, again, it's sort of almost common sense in a certain sense. Given two sets, A and B, one of these has to happen. The cardinality of A is less than B, or cardinality of B is less than A. And if these two are exhausted, what do you suppose has to happen? What seems to be left? This is called the comparability theorem. Basically, it says, look, I can compare any two sets. Two sets A and B, A smaller than B, B smaller than A, and if either of those are true, then they have to have the same cardinality. You cannot prove the statement without the following. So we call this, unlike the other ones, we call this axiom. I'm going to state this formally. If S is a collection of non-empty sets, then we can find a function f from this collection of sets into the union of these sets. there's this function. F from S. U. Such that F of A is for all A S. A. Okay. So let me try to wrap my head around this. What is this about? And why do I say that this is about choice? Here's my big collection of sets. Bunch of sets. Then there's a function from this collection of sets. This is where I'm making my choices. And the union of all the stuff in the set, right? These are all the sets A in this collection of sets. Such that given any set A, F of A is actually in subset A. So what I'm doing is I am making choices. Let me kind of diagram this. So suppose I have a large collection of sets. What does F do? F goes into A1 union and A2 union. And by the way, this is, I am writing this specifically countably many sets. It could be much more. I just want to illustrate what this is saying. So there has to be a function from S into the union of all these things, such that given any A and S, F of A is in A. So given any A1, F of A1 has to be in here. What is it? A1, it's an element of A1. And this is what I mean by making my choice here. F of A2 is an element of A2. So this is what this is why this is called the axiom of choice. And basically what it says is if you basically intuitively what this says is if you have any collection of sets, you can go through and make a choice out of each of these sets to pick an element. So let me give you a theorem that so we're going to use this axiom of choice here, and I'm going to finally take care of something I've been promising you for a while. So theorem. Let AN be a collection of pairwise disjoint denouement sets. So I'm finally going to put this to bed. I've talked about this result, we have used it a little bit, that of the collection of pairwise disjoint. pairwise disjoint enumerable sets is enumerable. So like I said, I've been dancing around this and saying, we're gonna get to this later, here's when we get to it. And we actually need the axiom of choice. So let's prove this. So what we need is we need a function. We need to show that this is in one-to-one correspondence with the natural numbers, right? That's how we show that this big union, it's a denumerable union of pairwise disjoint denumerable sets. I need to show that this is one-to-one correspondence with the natural numbers. So for all in the natural numbers, we select a bijection Fn from this one, n to a. Actually, for those of you that are fans of logic kind of things, we don't even need full axiom of choice here. We need what's called, and I bet you can guess why it's called, this countable choice, because the number of sets we have here is was in fact divisible. So we don't even need a more general axiom of choice. It's a countable choice. That doesn't matter. So what do I know? I know that every one of these ANs are denumerable, right? What does that mean for it to be denumerable? It's a one-to-one correspondence with the natural numbers. There might be many such bijections, right? But for every one of these sets, I pick the bijection, or I should say a bijection, that takes the natural numbers into AN. And now we define a function h from n cross n into the union. Yeah, this somehow I might do this. So actually, let me write this way. What I'm trying to do is build a function from the natural numbers across the natural numbers to this union. Might help to think of this way. How can I take my input being n and give me an output in this big union? Well, how about letting the first coordinate tell me which one of these A's to use? Right. And what do you suppose I use the second coordinate? So the first one tells me, okay, I'm going to select from AM. Then what do I do?
Select the n element of A.
That's essentially it, right? This tells me use FM because that goes from the natural numbers to AM. So this says, hey, use the nth one because I'm going into AM, and then choose the nth one of those. Right. Now, let's see if we can prove that this is a bijection. So this might be a good exercise. Let me remark that this function is in fact a function, right? Because we've got a well-defined input. There's no ambiguity on what our output is, right? You go to the nth one of these and pick the nth one in a line, right? Everybody okay with this function? How about onto? Let's do onto first. Let X be in the union AN. I've got to find something that goes to it. Okay. How can I go about that? What does it mean for X to live in this union here?
It's in one of these sets.
So X is in AM for some M in the natural numbers, right? But you can even go a little farther than that. Right? Actually, it doesn't matter, but we don't need this for this part of the proof, but it's actually only A. Why? They're pairwise disjoint, but there's no overlap. You can live in Massachusetts, you can live in Florida, you just can't live in both. That's the rule for the disjoint. But it doesn't matter here. Since X is in AM, there exists N in the natural numbers such that X is equal to F. Because this thing's a bijection, right? So here my subscript should be M, because we're going from N to AM. And there's some N that goes to it, because X is one of these people, so it has to be in the range of this. Hence, X is equal to F M N, which is H, check window. So any X is in the range of that, or H is. Okay. Okay, how about 1 to 1? One to one, I think we're going to have to use this disjoint. Suppose this means that F of N F A of B, right? Now let's think about what this means. This is a function that takes a natural number and it barfs out something in AM, right? And this, something in A sub A. So this thing actually lives in A sub M and A sub little a. What can I conclude from that? Good. Otherwise, if M and A are different, then that intersection is empty. Right? So now we've got that way. So we have that M and A are the same. So F M N equals F M B. What can we include from this? M must be why? All these functions are bijections, so in particular, they're one. So what do we have? Well, what we have at this point is M equals A, N equals B, so M A equals N B, and so H is 1. Now it's very subtle the way we use this in here, but actually right here we use the axiom of choice, because what do we have? we have infinitely many sets. And we have to choose bijection that goes the natural numbers to an for every one of these. So here's another one. Let's see if we can talk about what this might use the axiom of choice. There. Theorem 554. If there exists a function from the set A onto the set, we've been using this before, but I want to bring this up because this one actually requires choice. If this is onto, then okay. Let's see if we can show this. What does this mean? Our conclusion is cardinality be if less than cardinality. So what do we have to do to demonstrate that? What is that? What does cardinality be less than or equal to cardinality they mean in its most basic?
Cardinality B cannot be driven by cardinality A.
Right, but what is the very definition? So if I were to try to answer this challenge of showing that this is less than or equal to this, what do I need to show? That there's a function from B to A that is. To show this, I need to show there's a function from B to A that is what? 1 to 1. Okay. Let's say G. Such that G is 1 to 3. That is my goal. How can I do this? And why does it help that this is on to?
The fact that it's on to means that there's that you can find that every element is related to find.
Okay, so since F is on to, and for all B and D, F inverse, well, there exists A and A such that F A is B. Everybody good with that? So another way you might think about this, and you probably think about this in homework, is F inverse of B is not in. Remember, as a reminder, F inverse B is the set of X in A such that F of X is in the set B, which in this case means equal. Given anything in the codomain or something, it's in the range. That is something in A, right? So this is not part of my proof. This is just me attempting to illustrate. So let's This is a whole bunch of orange dots over here, maybe. Everybody agree that's an onto function, right? You got all kinds of things just piling on here. Right? How do we define a function? So right. How would I choose? Where should G take this thing? Well, there's actually three things in this particular case. They go to this first point right here. I mean, actually, it could be infinite. I didn't have time to draw that many, but so we'll settle for three. Yes.
Wait, so is G defined from B to A or A to
No, G is defined because that's what I'm. You know what? You're right. I wrote this wrong. Right. That's the mistake right there. I need to find G from B to A. Thank you. Notice, can I send this to all three of these? How come? What's wrong with that? It's not a function. To make this a function, I have to make a choice. Right? So I'm gonna let G of B be A sub B, where A sub B is a chosen element. In the previous set of these. Notice I have to make a choice. And actually, if there's infinitely many of these B's, I will have to probably make infinitely many of these choices. Right? And so that's where the axiom of choice comes in. I have to, I'm making potentially to prove this theorem in all its generality, I'm potentially making infinitely many choices. Is this a function? Well, I think I'm gonna sort of go back to my old sort of relations notion. So let x, y, and x, z be g. Right. I need to prove the y, z, right? So how do I move forward here? I need to show that g is a function, right? I need to show that y is z. This means both y, c are in, because what this means is, of course, y, z, or y, x that is, and dx are in F. Do I agree with that? Because this is the role of AB, and so if these are the same, or I'm sorry, X is the role of B here, and Y and Z are AB. So that means that both YX and ZX are in F, right? So Y and Z are in, right, so this is. Yeah, yeah. So these are both in, A, but. So. And Y equals Z by our choice, right? Because what did we do? Y and Z are both in F inverse, but we've chosen one here, right? And so basically, all this, the content of this is really, since we chose only one preimage, we actually get a function. Why is it 1 to 1? Now suppose. GU equals GV. Well, this means, so. BA, RET. This implies that AU, AB are in F, but F is a function. Actually, we probably could have used some earlier stuff in class to do this. So that, so here's some consequences of the axiom of choice. So the axiom of choice among some people, especially strict constructionalists, can be a bit controversial. However, most mathematicians, in fact, almost any mathematician that works with infinite sets, will believe in choice in a certain sense. So it's intuitive, right? If I've got a bunch of sets, I can just pick up the set, right? Consequences. This is called Zorn's lemma. If S is a partially ordered set, such that any wholly ordered subset of S has an upper bound in S, then S has a maximal element. In my own particular brand of research, this result is fundamental. And it's common sense, is it not, right? Because what it says is, suppose I have a partially ordered set, right? We work with these. And suppose that when you look at any totally ordered subset, all apples, if you will, there's an upper bound to that set of apples that's still in the set S. So the set S must have maximal element. You think of it as the union of these apples. Don't try to prove this in there. Yeah, it's equivalent to the axiom of choice. You have to have a choice. Here's another that's makes it seem really nice. Two, any product of a collection of non-empty sets. It's non-empty. Well, let me point out that if you have finite sets here, then, or I'm sorry, if you have a finite collection of sets, then this is pretty easy, right? I mean, if you have A equals 1, 2, and B equals AB, then 1A is in A cross B, right? There it is. In fact, I wrote it down specifically. This says that, what if you have more than two sets, right? A1, A2, A3, et cetera, et cetera. What if you have even larger than the numeral collection of sets? But I mean, doesn't it seem obvious that if you have a whole bunch of non-empty sets, then all you gotta do is fill in a slot, you're making a choice. That is actually the active choice. The fact that you can choose a coordinate for every slot, if you will, requires choice in the infinite case. These are two consequences. We can choose anything we want out of the collection of sets. If you have a set where every totally ordered subset has an upper bound instead of maximum element, any collection of non-empty sets is non-empty. But there are other consequences. Here's another consequence of choice. Three. Every set can. Well, this one is, oh, this is kind of a good blast from the past. Somebody remind me what it means for a set to be well ordered.
Was that when these two elements were related to each other, they are the same element, but otherwise the element is either greater than or less than its other element?
Well, so what it means to be totally ordered, or I'm sorry, well ordered, is it's totally ordered, right? So everything's apples, you can compare everything. And any non-empty subset has a smallest element, right? Every set can be well ordered. Can you name me a totally ordered set that occurs naturally that is not well ordered? Can't have the integers. Does the integers have the smallest element? That's a subset of integers, right? How about the real numbers? The real numbers are kind of worse, right? Because even if you take the subset of real numbers that are positive, there's no smallest element, right? You should be able to take the integers. Well, with the integers, I can do it. You should be able to take the real numbers and well order them. Now think about how you would do that, right? Because now you would have to have any subset, say all the positive ones have a small element. You can't order them in the way they're naturally ordered, because the way they're naturally ordered, it's not a well-ordered set. Positive reals has no smallest element. All the reals, no smallest element. You ought to be able to reorder the real numbers in such a way that any subset, including, so there should be some smallest real number. That is not so clear. You can get that right. And this is one of the things that makes the axiom of choice perhaps a little controversial. I probably shouldn't tell you this one, but anybody ever heard of the Cantor-Schroder-Bernstein paradox? You've probably looked that up, but you can use the axiom of choice in the Cantor-Schroder-Bernstein paradox. Take a ball, say in orange, and cut it up into a finite number of pieces, and reinsert those pieces together and make two balls of the same size as the original. That is a little disturbing. However, the proof of the Cantor-Schroder paradox that you could do this uses something called non-measurable sets, which is something you wouldn't be able to physically do anyway. Right, so there's that saying. So the axiom of choice, although I am a big believer, does have its controversial moments. Let me give you the last couple of things that, here's one right here that's in my choice. I had a graduate student. This one used to get really angry about this one. Theorem 555. Every infinite set has a denumerable subset. Now, let me tell you what the harm is in this, right? Certainly if I give you a specific set, like the natural numbers, it's got a denumerable subset, the natural numbers itself. But what if I give you an abstract set that's infinite? How do you know there's a denumerable subset? Well, how would you go about this? What do you know? You've got an infinite set. So pick an element out of it, right? And put it over in the corner, right? There's your first element of my denumerable subset. Pick the second element and put that over here. Pick the third element. And you never run out with this process, right? Because this set is infinite. But you're making a choice. You're making many choices. You really can't do this one without the axiom of choice either. And I don't know about you all, but I want all my infinite sets to have a denumerable subset. Any example that you think of will be of this case. The rational numbers has the natural numbers. The rational numbers itself is denumerable. The real numbers has the natural numbers in it. It's a denumerable subset, etc. And I think that's all right. So anyway, so that's the axiom of choice, and that's kind of for your culture. Now, we're going to, in the last bit of this course, I'm going to do a couple of sections. I call these modules. How many of you are taking 4120 sometime in your future? All of you should. It's abstract algebra. Anybody taking analysis, advanced calculus? I'm going to do a couple of little modules where hopefully I'll kind of break you all into that. But I want to start with something. How many of you have ever heard of a group? Like a mathematical group, right? I have a question. A group is basically a mathematical structure that consists of a set of elements and a way to combine them, right? For example, the easiest example I can think of is the integers. I've got a way to combine those, take two integers and add them up. Still an integer, isn't it? And it's got a couple other things. It's got an identity that is something that leaves everything alone when you use it to operate. What integer can you add to any integer and it leaves it alone? 0, right? And every integer should have something that takes us back to that identity. What can I add to, say, 5 to get to 0? -5, which is an integer. Right? This is basically what a group is. Now, I'm going to start you with this question here. How many of you have played with it? Solve it? Let me ask you, suppose I do something to this cube and I write it down, so I'm careful about it. I do something to this cube and then I do it again and again and again. Will it come back to its original pristine solved position? Well, let's try it. Okay? How about this? 1. Once, twice, 3 times, 4 times. Oh, what a shot. Right? Let's do something more exotic. How about this? What if I do this? And this? And this? What if I keep doing this? Am I ever going to come back again? How about how many of you think that I'm going to eventually get back to where I started? How many of you think that maybe I won't? How many of you voted based on the fact that time is almost out for the class today? Right? So let me, here, this is, group theory is about patterns. Do y'all see every so often I get a cross like this, and every so often I get, the corner, right? I agree with that. But here's the thing that concerns me, and that is, maybe I'm kind of like, maybe I'm like in the toilets here, circling bowl, right? Maybe I'm repeating things over and over again. I mean, how do we know that I'm not just repeating messy patterns and, oh, there's a pesky cross again, I'm just kind of doing things over. Can anybody make a case for why I am or am not in an eddy? Besides the fact that class is almost over? Well, that's one of the things that group theory is about finding these kind of patterns and symmetries. And they show up in nature. And here we go. Now, how many times did that take me to do that? That particular cycle took 105 times. Anybody able to solve this? I'll tell you, one of the reasons it's hard to solve is look at this operation X. I'll call that X and that Y. X, Y. See what that one's like? Now, Y, X. Is it the same? Order matter when you try to solve Q. I will teach you enough abstract algebra problem work where you can solve this with pencils. More next time.